This is an example problem from Chapter 2 of Matter and Interactions. We're asked to predict the motion of a mass and spring system for 0.3 seconds. The spring sits vertically on a flat surface. It has a relaxed length L0. We push the spring down and put a massive block on top of it, and then release it, and it should oscillate up and down. Now, our plan for doing this is always the same. We calculate the net force, we use the net force to update momentum, we use momentum to update position, and then we do it again using the new position. But if we'd like to implement this in VPython to do an iterative calculation, we need to make a more detailed plan. So our plan is going to be to calculate the net force. We need to calculate two different forces. We have the force from the spring pushing up, and we have the force, gravitational force by the earth pulling down, and we need both of these forces. So we need to start by calculating the spring force. And to do that, we're going to need the vector L, which points from the base of the spring, the fixed end of the spring, to the movable end. And we're going to need to get that by vector subtraction. It's basically equal to the position of the block relative to some origin minus the position of the base of the spring. And we can use this now to get the stretch of the spring. That's going to be equal to the current length, which is just the magnitude of L, minus the relaxed length of the spring. And now we can calculate the spring force, which is equal to minus the spring stiffness times the stretch times the unit vector L hat. So this piece of our plan is to calculate force by the spring. Now we need the gravitational force, and that's an easier one because it's not varying. It's only in the y direction, and it's equal to minus the mass of the block times little g. So that gives us the gravitational force. The net force is going to be the sum of these two things. Now we can apply that to update the momentum of the system. The momentum of the system a short time in the future is going to be equal to its momentum at this instant plus the net force delta t. So this is update momentum. This is calculate F net. Then what we're going to use is the new momentum to get an approximate value for V average over this interval. We'll take P final over the mass, and so we can apply the position update equation to find the new position of the block. A little time in the future is the position of the block at this instant plus V average delta t. So that's update position. Since we're doing an iterative calculation, we're going to need to update the time. So time is whatever it was plus delta t. And now we're ready to repeat. Go back up here. And the key about this repetition is that now this value of our block has changed. What we're going to be using is this final position here to get a new stretch and a new, therefore a new spring force. So that's what we need to do. We need to follow these steps in VPython. In VPython, we start with some initial values. From the problem, we're given that the mass of the block is 60 grams, the spring stiffness is 8 newtons per meter. The relaxed length is 20 centimeters. We're going to set the position of the base of the spring, the ground, at 0, 0, 0, and we know that the value of the Earth's gravitational field near the Earth's surface is 9.8 newtons per kilogram. We also need initial values for the position of the block. We know that that's at the top of the spring. The spring is compressed to a length of 10 centimeters, so the position is 0, 10 times 10 to the minus 2 meters, 0. And the momentum of the block is initially 0 because it's at rest. We also need to initialize our value of time. So we'll start time running at 0, and we'll pick a time step of 0.1 because that's what we're asked to do in the problem. In the problem, we're asked to predict this motion for 0.3 of a second in time steps of 1/10 of a second. This tells us what the condition of our while loop should be. We want to run as long as we haven't exceeded 0.3 of a second here yet. And we're just going to follow our plan. So the first thing we need to do is calculate the spring force. To do that, we have to calculate the vector L, which is the position of the block minus the position of the ground. This is what we call the position of the base of the spring. The stretch is, just as we said, the magnitude of L minus L0, and now we have a value of the force exerted by the spring. We need the force, the gravitational force by the Earth, and that's 0 minus mg, 0. And the net force is just the sum of these two forces, F Earth plus F spring. So now we've calculated F net according to our plan. The next thing we need to do is to update the block's momentum. So we'll update momentum. We will use that updated momentum. So P block is P block plus F net delta T to update the momentum. We'll use that updated momentum to approximate V average. We'll take this new value of V block, divide by the mass to get the velocity, and now we just use the position update equation, our block plus V average times delta T, and we'll update the time, so we don't want to go past our stopping point. And now we're ready to print various things. We can print how much time has elapsed. We could also print various things that we've calculated here. So we can print the vector L, the stretch, the spring force, the force by the Earth, the new momentum of the block, and the position of the block. So all we've done is translate our plan into VPython. Notice we haven't bothered at this point with any animation. We're just doing numerical calculations. We run the program, and it prints out various things. We see that with a time step when t is 0.1, the position is now 13.5 centimeters above the base. Time is 0.2, the position is almost 16 centimeters above, and time is 0.3. It started to go down, so now it's about 14 centimeters above the base. If we actually we didn't have an animation, but if we wanted an animation, we could add that pretty easily. We could add a box to represent the block, and a helix to represent the spring. So here's our block represented by a box and a helix represented by a spring. And down here, after we've calculated the new position of the block inside the loop, we need to update the position of the block here. So we'll use our block to make that the new position of the block, and we recalculate the extent of our spring here. And if we do that, we probably want to put a pause in so we can see the animation happen. If we do that, we see that we can step through it. The spring stretches and then goes down. But now that we've got it in a loop, we can actually make this run longer and look nicer. So let's let it run, instead of for 3/10 of a second, let it run for 5 seconds. And we'll put in a rate command so we can see this happen. We'll take out the pause because we aren't going to need this. And if we run this now, we see the spring go up and down.